folks. I shot this first segment about 3 times and I wasn't happy with it, so let me reiterate. I'm going to try to basically upload recordings to YouTube. I have had little success with live streaming. I don't seem to have the authority to do that remotely. I can do it from my apartment, but if I were to do that from my apartment, unfortunately I wouldn't have a board or anything and I was projected to do my regular work. So anyhow, the plan tentatively is that I will come here either before or on the days that we are regularly scheduled, record the lessons, and then hopefully upload the entire thing. And that way we'd have a little bit more choice about when you want to watch it or turn it off even, right? And use it whenever you need to. Anyhow, let me get started. I made a little bit of agenda like I normally do. All right. The calendar has to be adjusted naturally. We'll assume that this is temporary, the situation, that we will be back in April. Anyhow, in the syllabus that you were given in the beginning of the semester, there was naturally the calendar, so let me pull that up first and we'll talk about that. I'm hoping that the audio quality is just decent enough that you can hear me from the distance that the camera that I have is at. Unfortunately, it needs to be where it is, and I don't have an external microphone either. So bear with me, please. Anyhow, let me pull this down. Let's talk about the schedule. This was the original plan. And if we had come back, I was behind a little bit before the break. I basically finished with section 2.5, which was our Venn diagrams chapter. And now we're starting with chapter 5 from scratch. Anyhow, what I had done initially was intend to put 5.3 here on Wednesday, which is technically tomorrow, the 18th. And cover the sections 5.1 and 5.2 here. Since we didn't have class on Monday and I was behind a little bit to begin with, I'll have to probably nix this review day. At any rate, what I'm going to do now is do sections 5.1 and 5.2 for this, the 18th of March. Actually, I made a packet, but I can't give it to you. So let me at least show you what the contents of the packet are. If you go into our Canvas and go to Pages as always, and go to MAT-113 Materials for Test Number 2, which is forthcoming. Hopefully we'll have it on that day. We'll see. I put this in yellow, sort of orange. All right. What is in orange? Basically, these contents here would have been the packet that I had prepared for this lesson. All right. Basically, there is a diagram that includes information about prime and composite numbers, all right, to distinguish them. All right. On the second page, there is some rules of divisibility. And then 2 methods for obtaining the prime factorizations of 2 or more numbers for the purpose of determining a GCF, greatest common factor, or your textbook calls it greatest common divisor. Same difference, same product. Stupid joke, sorry. Anyhow, well, least common multiple, right, which is not called anything different. Let's see, and the last page is a diagram of basically what I like to call a numbers family tree. Right? It's to help you distinguish different types of numbers. Right? There is another sheet of paper which I did not connect to this, but I will point to now, which is that same diagram I had been using when we start our chapters that are for terminology. Right? Whatever abbreviations, whatever symbols that correlate to that. Right? So you could get this from the same page in Canvas. It's concept, symbol, definition, table diagram, right? I just didn't group it into this because it was already established. Anyhow, if you're at home and you have access to a printer, maybe print these things out, right? There, as of right now, is a computer lab on the campus that you can come to if you need to. The IRC 241, the building basically in between the library and the Johnson Learning Center, is the regular, main computer lab for the campus, right? That we still have access to. Just be prepared when you come. You have to have your ID, student ID, ideally, and they'll kind of space you intentionally far apart from any of the other students, just for the safety precaution, not to spread germs, whatever. Anyhow, let me start with this, and we'll get busy. And if I can, I'll try to get it done in under the time frame of an hour. I don't know really if YouTube is going to let me send a file of this size. Right? Strangely, if I had done a live stream, it could have been any length of time. Right? I'm hoping that they gave me greater capacity, but we'll see. Anyhow, have this, or maybe just take out your notes, and I'll pull this up over here. I'll give you some reminders a little bit later, but let's get started. Maybe I'll get the terminology entirely out of the way first. Let's see if I can put this up on the board here. Incidentally, if you want to, in your notes, to sort of fold over a little divider, this is chapter 5. Chapter 5 is officially number theory and real numbers. Sorry again for the audio. I will try to project my voice as best I can. Family, if they see this unfortunate material, will go, yeah, it projects his voice all right at home all the time. Thanks. All right, let's start with this. First of all, just to clarify what is number theory, there is no symbol for this. Just the concept of number theory is basically the study of numbers and their properties. Straightforward enough, right? I don't want to repeat the same thing too much, but we had discussed, right, to this point, natural numbers. And since I have to compare it to other things, mention it again. You already have this, at least in 2 places. Natural numbers, which are usually signified by the capital letter N, at least when you talk about sets of natural numbers, are the counting numbers, the kind of numbers that you could count on your hand, right? So officially, you would see them in fancy braces, 1, 2, 3, 4, 5, and then ellipse marks to indicate that they go on forever, all right? The whole numbers, they are technically whole numbers, but that is another category as well. So they refer to them as the natural numbers because they're the kind of numbers that you can count. On your hand. Right. You don't usually count negative numbers on your hand. I suppose you could adapt some system, but that isn't natural. Then there's this term, factors. Factors are, for now, natural numbers multiplied. To sort of give you a visual cue of what is being implied here, I'm just going to use these question marks. When you have basically two numbers that are being multiplied, and they are technically natural numbers, those two numbers, whatever they are, that's the question mark, are factors officially. Right? Again, your textbook, for whatever reason, also refers to them as divisors. Right? From the perspective of division, which is just the opposite of concept of multiplication, no harm in saying that, but I think factors is sufficient. Right? Usually, when you're talking about division and divisors specifically, right, a divisor is a number you divide by, of course. I'm just using the colon with the line to represent divide. If you had any of the three styles of writing division, let's say you had the traditional division box, the divisor would be the number that is sitting outside the box. Right? Or it would be the number underneath the sort of fraction bar style of division. Or if you just went with the regular colon with the line, it would be on the right side of that symbol. Right? The dividend is officially a number you divide into, for lack of a better expression, using the divisor. And that has to sit here, on the inside, or on top, or on the left. Then there's this concept. We're going to get into the subject of divisibility. I have my own sort of definition, but I'll give you the more textbook definition if I can. When you have this situation, when A divides B nicely, and A divides B, incidentally, is this symbol. A line, a vertical line with an A here and a B here. It unfortunately sounds similar to this, which is, I'll put a little thought cloud here, A divided by B, which is usually symbolized by a forward slash and then the letter B rather than a straight line. It's not super important, but if you come across this in instructions and they start saying things that sound a little awkward but similar to this, they're trying to draw some kind of distinction. What I mean by this, when A divides B nicely, it means that there is no remainder. You just get a natural number, technically a whole number is feasible, for an answer. Here's an example. If you had 24 divided by 2, right, you would say that 24 is divisible by 2. Because the result of dividing 2 into 24 is that you're going to get a whole number for an answer, namely 12, right? If you did it piecemeal, 2 goes into itself exactly 1 time, and the difference would be 0 if you subtracted them. You do home division. And 2 goes into 4 exactly twice, right? That's 12. And you get a 0 for remainder. Notice that, although it's sloppily written here, that's 0 for the remainder. For all intents and purposes, that is to say, no remainder then. All right. If, on the other hand, you had something like 25, you would say that 25 is not divisible by 2, right? Anything, well, 25 can be divided by virtually anything, with the exception of 0. Nothing can be divided by 0, it's undefined. But virtually almost everything can be divided by something else, right? But you might get a remainder in some situations. To say that something is divisible is a little bit more specific. It's saying that it divides nicely, for lack of a better expression, but you get a feel for that. When your result is not something cumbersome, no fraction, no decimal, no remainder, or 1, or what have you, as you see in this case. 2 goes into 2 exactly 1 time, as before, and the result is still 0, and then bring down 5 and repeat the process. And 2 goes into 5 roughly twice, because it's close, and you get 4. And in this instance, you get 1 as a remainder. Now, granted, and you're probably aware, if you were doing decimal division by hand, yes, you would put a decimal point in the 0, bring it down, and it would eventually terminate. You get 12.5. If you were making a mixed number, right, this 1 that is the remainder would be your numerator. And this 2 that you're dividing by would be your divisor. It would be 12.5 in that style of doing it. However, we're not really looking to do that right now. We're really just discussing this concept of divisibility. Realize that this is referring to it. A divides B. When you see that written in context, right? And when A divides B nicely, right, that means that it has no remainder and it is divisible, right? 24 is divisible by 2 because it divides nicely, right? You get a 12 whole number essentially from the answer. No remainder is the bottom line. Basically, most things are dividable, right? But not everything is divisible. Make that distinction. Again, let me get all of my terminology out of the way first, and then I'll start giving you some examples. I'm looking at the clock when I really should involve it, but it doesn't. Let me erase this. Just for reference, to reiterate that last statement, kind of remind yourself of this, right? Most numbers are dividable. Right? Not all are divisible. Essentially what that means is that when you attempt to divide, you're not always going to get a remainder of 0. You're going to get something that is a remainder. All right, 1, 2, 3, whatever it is. All right, sticking with this. All right, prime numbers. All right. I did give you a hand. Well, I didn't give it to you, but I made a handout which I'd like to point at now. Here's the textbook definition of a prime number. This will be important later, especially when we get into fractions. It is a natural number. Greater than 1. And has only 2 factors. Sort of brainwashing that I remember is a more concise statement, which said that it has only two factors, one and itself. I'm sure that you probably had similar brainwashing growing up as I have. Usually it is in tandem with the concept of prime numbers that they talk about composites. Composite numbers, all right? It is also a natural number. It's very faint, sorry. A natural number that has two or more factors. That's important. That has two or more factors. But technically, not infinite. Less than infinity. Then there's prime factorization. I'm sorry, I have to get the dry stuff out of the way. Basically, the prime factorization is the product expansion of a number using primes only. So for example, what you're inclined to see is you have some original number, whatever it is, and the prime factorization is a bunch of numbers written with intentionally the multiplication x, so sometimes it's just the multiplication dot, all right, lined up like so. All right. That bottom rung of factor tree, which you're probably familiar with and we're going to get into in a bit, all right, has to be expressed exclusively in terms of prime numbers. Right? Now you might wonder, well, what are prime numbers? There are some that you can memorize, right? They're good to look for, but there's also techniques for deriving them. Anyhow, last two things and we'll get to the more interesting stuff. A whole number is pretty basic, right? A whole number is distinguished from a natural number. That's really the reason that I'm mentioning it. There's no real abbreviation for that. What you would see if you saw the set of whole numbers is one very obvious distinction. I'll put natural numbers underneath it again, just for visual aid. If you were to compare the list of natural numbers, they start with the number 1 and they go into infinity, right? Which is what the ellipse marks are indicating. That this is, beyond just stopping at 5. All right. The whole numbers include the number 0. Right? That is the distinction between a whole number and a natural number. Natural numbers, like I said, if they're natural counting numbers, and you can think of your hand as the sort of numbers that you can count on your hand, you generally don't count 0. Right? You start with 1 when you count with your hands or your toes or what have you. The natural numbers would start at 1 for that reason, but whole numbers have a 0. Then there's the integers. I'm going to squeeze in here. The integers are an increasingly large set. So, sticking with fancy phrases here, set notation, I'll put this here. They are whole numbers that include the negatives. So let's just say, I'm going to start with 3 to make it obvious. -2, -1, -0, +1, +2, +3, more ellipses to follow it. To distinguish integers from just traditional whole numbers, right, they include 0 as well, as you'll notice, but they also include the negatives. Right? Essentially, integers are negative or positive whole numbers and 0 also. Now you might be wondering, well, I've seen negative fractions or I've seen negative decimals. They are a negative number in those examples, but they're not officially an integer unless they are a whole number. It's technical, right? Now that that's out of the way, there's no really other terminology. Let's move on. Okay. Let's say that you had to figure out all of the prime numbers from 0 to, say, 50. You could attempt to do it brute force, or there is a method we're going to discuss. Before I do that, let me flash this diagram that I had mentioned before. This is to summarize basically what we're talking about, primes and composites especially. Primes, a prime has exactly 2 factors, 1 in itself, whatever that number is. The number 1 technically only has 1 factor. Now you might say, well, isn't it 1 times 1 that makes 1? Yes, but it's the same digit. And if you had to basically list the factors, you are only obligated to write unique factors, just 1 time each. So like even in the case of number 4, for example, notice that the factors of 4 are indeed 1 times 4, but the other pair famously is 2 times 2. You don't write the digit 2 twice. Once is enough, it's accounted for. Anyhow, 1 is its own category. It is neither prime nor composite. Primes, 2 factors, 1 in itself. Composites, more than 2, but less than infinity. There is, in theory, one number that has an infinite number of factors. 0. Because 0 times anything, including itself, is 0. All right, so think of this as being 4 distinct categories, if you will. Right? And these especially are going to be good to know. They are another example of something that, in the long run, you probably want to memorize it so that you know what to look for. You'll have a pattern in mind, right? And it would be good to know basically just these 2, 3, 5, 7, 11, and 13. Right? Those are not too hard, they're pretty familiar, right? It's impossible to memorize all prime numbers, right? Believe it or not, this is the pastime of many a mathematician, you know? It's like memorizing places of pi. But you're certainly not required to do that. Anyhow, let me give you a method for determining primes between 2 an endpoint